back. This is lecture 14. So in the previous lecture, we talked about ways and means of ensuring that most of the current that we want to get from the input pair or from the antenna actually goes to the output, while recognizing the fact that there is a problem with respect to the current getting divided because of the parasitic capacitances. And taking pulling onto that thread, we also saw there is some fundamental limits of a transistor, simply because there are some capacitances associated with the transistors which divert the current from the comes from the source, that is the antenna, in a common gate configuration. And we could relate that to the transit frequency of the transistor, right? We could relate the amount of current that will ultimately go to the output to the transit frequency of the transistor. And then we saw that this transit frequency, that is Gm over Cgs, actually should be Gm over 2 pi times Cgs, it appears in many other forms also. For example, we saw that if we assume a common source amplifier, one common source amplifier driving another identical common source amplifier, it is up till the transit frequency that you can expect to get a voltage gain of more than 1. Or if you just simply take a common source amplifier and you push in a current, and that current will essentially, a high frequency current will generate some voltage at the gate of the between the gate and the source of the transistor, which in turn will develop some current at the output, and that ratio of the current, if I associate the gain to be the ratio of the output current to the input current, then again the current gain you will also get a current gain of more than 1 till the transit frequency of the transistor, and everything boils down to the ratio of Gm over Cgs approximately, right? So given that this transit frequency of the transistor seems to be a very important, it seems to be an important limit till which our circuit can work, right? Obviously, our circuit, you cannot really take your circuit to FT, you have to stop well below FT. But if you know that one MOSFET has an FT of 100 gigahertz, another MOSFET has a FT of 200 gigahertz, then you know that the one with 200 gigahertz will be more useful for design of my high frequency circuit than the one which has 100 gigahertz, or maybe one which has like 50 gigahertz or so, right? So given that we understand the importance of FT, so part of this lecture is to go through some amount of device equations to understand what we can do as a circuit designer, not as a device designer, as a circuit designer, to maximize the FT. Okay, so let's in that vein, let's get started. So let's say again, I assume we have a common source amplifier. It has been biased, it has some VGS, it has some VDS, okay, and it has some quiescent current IDSQ that is flowing through it. If I use our textbook saturation current equations for long channel devices, then we know that your IDS is essentially, I'll just drop the Q because we are doing quiescent anyhow, UN Cox W by 2L VGS minus VTH whole square. Again, I am neglecting channel length modulation because when we are only considering the effect of GM, the channel length modulation does not play a dominant role, right? There is some role, but it's not a dominant role, so we'll just put it aside for the time being. So what is your GM? GM is del ID dou IDS dou VGS, which is nothing but UN Cox W by L VGS minus VTH, right? And what is my FT or omega T? Omega T is Gm by Cgs, Now, what is CGS? We understand what GM is, but what is CGS from a device perspective? So again, we go back to the cross section of a device. Again, I'll go back to the most simplest cross section of an NMOS transistor. Most simplest form of NMOS transistor. N plus, this is N plus, this is P minus. I am not showing the body bias, but it is assumed, okay, it is assumed that the body is grounded. Okay, so let's say this is the source, so this is the drain, the gate, right? If it is in saturation, right? Firstly, it has to be on, which means I have a positive voltage between the gate and then the source, and I also have a positive voltage between the source and the drain, and the drain is a sufficiently high voltage above the threshold voltage of gate, so that we do not have a problem with linear region. All those things we understand, but the key thing to understand here is that we have a we'll have electrons in the channel, right? And if we are in under the condition of saturation and pinch off, then the mobile electrons will have kind of triangular well shaped distribution in the channel, right? Okay, so I will remove all these batteries for the timing. So what is the what type of capacitances are we looking for here? So if I instead of only looking at the cross section in this manner, let me try to draw a pseudo 3D section for this MOSFET. So if I extend this gate in the other dimension, then we understand that I will use a different color for the doping of N type. So this is the N doping. And you have the drain coming from somewhere here. Similarly, you have the source terminal coming from somewhere which is not visible here, but on the other side, and probably the gate is connected somewhere here. Right? Let's assume the gate is connected. Okay, physically, in actuality, this is not how it is connected, but I mean, you get the idea. Okay, so now we have these electrons here. Okay, so now what is the capacitance that we are looking at? So clearly, so the capacitance that we are looking at is, so let's look at the physical capacitance that is always present regardless of the operating condition of the transistor. Okay, so the capacitance that are always present is obviously the overlap capacitance between the gate and the drain and the gate and the source. Right? What do I mean by that? So if I concentrate only on this part, if I concentrate only this part of the cross section, where there is a slight amount of overlap of the gate and the drain, right? So on the gate side, you have polysilicon or metal, and N plus is also conductive. So basically, you have conducting material, you have a insulator, and you have another conducting material, which means that it's a parallel plate capacitor, but the plate width is only that overlap part, right? So you are going to get a capacitance because of that overlap. What will be the value of that overlap? Rather, what will be the value of the capacitor? So, so the, so the plate is essentially, the plate has this entire, so this plate is, the plate has this length, or the longer dimension of the plate, essentially the width of the transistor, right? So this is the W of the transistor, this is the L of the transistor, length of the transistor. So you have an overlap capacitance. So you have an overlap capacitance, or let me also make it explicit that I have a CGD overlap, which is equal to some unit capacitance, right, which corresponds to the amount of overlap times the width of the transistor, right, times the width of the transistor. Okay. Similarly, because your MOSFET is a symmetric device, the same capacitance will exist on the other side, on the source side also, right? So we are going to have a CGS overlap, which will be equal to C overlap times W, right? Where C overlap has the unit of capacitance per unit length, right? So this is basically farad per meter. Okay. Okay. Fine. What else? Now this amount of capacitance will exist regardless of the operating point of the transistor. Okay. Now let's focus on the fact that your transistor is in saturation, and let's say it is in saturation in such a way that you have just reached pinch off. It's a long channel device, and you have reached pinch off. Okay. So now if you have reached, it's not the correct way to draw the pinch off condition. Okay, so you have electrons here, it's filled with electrons. So now what is happening is, this is all electrons. So now what is happening is that you are getting an extra capacitance from the gate to this channel, and this extra capacitance is mostly between the gate and the source side of the channel, and then on the gate side, drain side of the channel. Firstly, because towards the drain side there is no physical connection between the channel and the drain, because there has been pinch off. So I can essentially apportion this entire channel capacitance to the gate side. And because it's not a rectangular channel, it's a triangular channel, right? So essentially the gate capacitance, the CGS total is essentially the extra capacitance that you are getting because of this charge that has accumulated under the channel, which is nothing but, if it were a rectangular channel, it would have been Cox times W times L, right? But since it's not a rectangular channel, if I make a triangular approximation, this becomes 2/3, right, plus the CGS overlap. Okay. So clearly you see that under saturation condition, the total capacitance, the CGS capacitance dominates over the CGT capacitance, right? And this I can also, the CGS, I mean, or the more accurate way of explaining that is, this capacitance dominates over this capacitance. This is generally uh, quite a few times more than the overlap capacitance. So you can, in most cases, under saturation condition, you can basically approximate the CGS capacitance to be equal to 2/3 Cox W times L. Okay, so why are we doing all these things? We are doing all these things because we are after Ft or omega t, right? So now that we have some setup, so what is omega t then? Since omega t is Gm over CGS, which is mu n Cox W by L V over drive divided by 2/3 Cox times W times L. By the way, and just for the sake of clarity, Cox is capacitance per unit area, right? So basically this is farad per meter squared. Okay, so basically yeah, so you'll have to be slightly careful with respect to the units. This overlap capacitance is per unit length and this Cox is per unit area, and the reason this is expressed in this format is because uh, the amount of overlap is not in a designer's control, is not in a circuit designer's control, it's in a device designer's control. But once a technology is fixed, we cannot really control this overlap, right? We cannot control this overlap. Okay, but we can control the L, we can control the W, and we can control the L. So for a designer, that overlap is not a design variable, but the length and the width are. So we would like to ensure that at least we would like to simplify this capacitance calculation in terms of the W's and the L's, and the rest we'll put in a constant or a proportionally constant, and the proportionally constant for the overlap capacitance will essentially be capacitance per unit length, and since the total capacitance between the gate and the channel can be controlled by both W and L, or it is basically a function of the area, and both dimensions of the area can be controlled. So hence the unit capacitance is per meter square. Okay, so that, I mean, that out of the way, let's concentrate on omega t. So this becomes, so here what you see that Cox goes out of the window, right? So what do I get? And W also goes off. So I get mu n 3 by 2 times V over drive by L squared, right? Or in other words, my Ft is 3 over 4 pi times mu n times V over drive by L squared. Now, do not get too bothered about this 3 over 4 pi times mu n, because that is not in our control, right? Mu n will be given by the foundry. It is the mobility of the electrons in this case. Whatever it is, it is. What is the designer variable here? The designer variables are V over drive and L, right? So in order to maximize my Ft, what do I need then? To maximize Ft, maximize overdrive voltage and minimize L. Now in a particular technology, right, when a particular technology is given, the minimum length that you can have in a transistor is also fixed, right? So if you are using, for example, a 180 nanometer technology, then 180 nanometer is the minimum L. If you are using a 90 nanometer technology, 90 nanometer is the minimum L. If you are using a 65, then so on. If you use a 28 nanometer, the 28 nanometer is the minimum L, and so on. So clearly, once you have fixed the technology, there is not much you can do with respect to the L. But as a designer, you need to ensure that if maximizing Ft is your goal, then you should not use a non-minimum L. If the foundry is, let's say, giving you a 60 nanometer minimum L, you always have the option of using 120 nanometer or 180 nanometer or higher, but you should not do that, because basically you see that increasing L has a seriously bad impact on the transit frequency of the transistor. And what is the second design variable? The second design variable is maximize the overdrive voltage, right? So essentially you'll have to ensure that you bias your transistor with as high a VGS as you can, but the natural consequence is that if you have a lot of overdrive and a lot of VGS, and if you have multiple transistors in the stack, then you might not be able to bias everything in saturation, right? So the practical solution is maximize V overdrive without really disturbing the biases of the other transistors. Okay. What is the intuition behind this? Why do I need to maximize the V overdrive? So note that FT is essentially GM over CGS, which means that, let's say I have fixed a CGS, I would like to have as high a value of GM as possible. Now, what do you mean when I say I have fixed a CGS? When I have fixed a CGS, what I essentially mean that I am not changing the W and the L of the transistor, right? So another way of writing this is to maximize FT, means for a given CGS, i.e. W and L, right? Once given CGS means if you have minimum L, the W is also fixed. We want maximum GM. Now, if you are not allowed to change W and the L and you want to increase GM, what is the only thing that you can do? You have to basically increase current, right? And how do you increase current? You increase the overdrive voltage, right? So, so both mathematically and using intuition, you see that under this simplistic, very simplistic long channel assumption that we are so familiar with from our undergraduate days, so we see that in order to maximize the operating frequency of the transistor or the transit frequency of the transistor, we have to ensure that your transistor is biased with as high an overdrive as possible. Okay. So the thing that also you should keep in mind is all of this we are doing while ensuring the transistor is in saturation. There's no point in increasing the overdrive so much the transistor goes out of saturation. That will defeat the whole purpose. So we have to also mention that while keeping sufficient VDS to keep the transistor in saturation. Okay, when I say sufficient VDS, you essentially, if I again go by the long channel approximation, then essentially we have threshold voltage VD should be greater than VG minus, the drain voltage should be greater than 1 threshold voltage lower than VG minus 1 threshold voltage, right? So this you'll have to ensure is simultaneously satisfied. Okay, so what I have done till now is essentially taken the long channel model of a transistor and gone through the requirements of how to ensure the transistor gets biased in saturation. How the transistor, while remaining in saturation, can be biased for maximum transit frequency. Now, as it turns out, as the channel length keeps on shrinking, right? The saturation equation of the simplistic saturation square law equation of MOSFET that we are so used to becomes kind of invalid, right? It's a very simplistic model, but surprisingly accurate and surprisingly gives us a lot of design intuitions. But as the channel length keeps on reducing, that is not exactly accurate. So what we will do next is to take another extreme case where the channel length has reduced so much that the velocity of the electrons is no longer dependent on the VDS difference, right? So what I essentially mean is this, right? So let's say again I'll draw the cross section of the MOSFET. So this is source, this is drain, and you have, when the channel is formed, you have you have kind of electrons spread across the channel, right? And you have some gate voltage here, and then when you increase the drain voltage, then you increase the drain voltage, the channel around the gate and the drain junction starts to get depleted, and you kind of get a triangular formation, right? You start to get a triangular formation, and at pinch off the kind of start getting a triangular formation, and at pinch off the channel totally vanishes at the drain side, right? Now think of it. Now can you comment on the concentration of the charges somewhere in the channel closer to the source with respect to closer to the drain? What I'm saying is that what is the concentration of the charges here with respect to here? So clearly the concentration of the charges towards the source is higher than towards the drain, right? Now can you comment on, if I sit here, if I sit at this cross section and I try to find out what is the current that is going in that direction, and I sit in this cross section and I try to find out what is the current that is going in this direction, what can you comment on? Is the current the same or different? The current is of course same, because there is a continuity of the channel, right? So given that the current is same but the concentration of electrons are different, what can be the only possible solution? The only possible solution is the speed of the electrons, the velocity of the electrons here. If I call this one, let's say I call this V1 and I call this V2. So clearly the speed of the electrons, or the velocity of the electrons at V2 is greater than V1, right? V2 is greater than V1 because why? Because if I call this Q2 or Q1, and if I call the amount of charge concentration concentrated around this snippet is Q2. So since Q2 is less than Q1 and I2 is equal to I1, and I1 is equal to I2 and Q2 is equal to Q1, therefore it makes sense that V2 is greater than V1, right? So from this intuition, what can we conclude? We can conclude that as the channel becomes smaller and smaller, right, here the velocity of the electrons become larger and larger. Now as it turns out, in a particular piece of silicon or in any particular material, the velocity, there is a maximum velocity the electrons or the carriers can reach. What happens if before the pinch off happens, the electrons reach that velocity, right? Then pinch off will obviously not happen because the electrons cannot move any faster, right? If the saturation velocity, if the velocity of the carriers becomes saturated and the current is constant, which means the concentration of electrons or concentration of the mobile charges will also not go down, right? If the concentration of the charges don't go down, there will not be any depletion. If there is no depletion, there is no pinch, right? So if the electric field in the channel, right? If this electric field becomes large enough, right? If this electric field becomes large enough such that the electrons reach a saturation velocity, then obviously you are not going to see a pinch off. And in an extreme case, right, where the channel is so short that slight amount of voltage between, like couple of 100 millivolts of voltage around VDS can lead to that saturation velocity, then you are not even going to see a rectangular channel. You are basically going to see almost like you are not going to see a triangular channel. You are almost kind of going to see a rectangular or trapezoidal or close to rectangular channel, and that is an extreme case, right? So if an extreme case, what I am talking about is if the channel is very small, right? Such a small channel is very difficult to be drawn, but let's say the channel is so small and you have applied a, I mean, it's in saturation, and there is charge formation in the channel, but the electric field here is so large. The electric field in this channel is so large that the velocity near the source and the velocity of the electrons near the drain both are high enough for the electrons to get saturated, because ultimately the velocity is what? Velocity is, I know that V is equal to mu times the electric field, right? So mu is the mobility of the electron, which we, if we assume it's proportionally constant, then it's essentially, all we have to ensure is that, if all we have to understand is that if the electric field has reached a saturation value, then the velocity also has reached a saturation value. And if the electric field around the source side has also reached the saturation value, then obviously the electric field at the drain side has also reached the saturation value, which means that the speed of the electron is constant throughout the channel, and the concentration of the electrons are also constant, approximately constant throughout the channel. And this is kind of a very rough, hand wavy intuition behind as to what can happen in a short channel device. This is called a short channel device, where short channel device under velocity saturation, right? So we should call this a short channel. I should always caveat it, because these are short and long are relative terms. Channel device under extreme velocity saturation, i.e., velocity is saturated at both ends, source and drain ends. Now note that this, just like you never have an ideal long channel device, you will almost certainly never have in design a situation like this. It will always be between a long and a short channel. It will be either between operating between the model on the top and the model on the bottom, right? But it's good to understand what are the limits of these models, right? So if I do this simplistic model, right, if I do this simplistic model for short channel device, then what is the drain current then? I mean, it becomes fairly simple. Drain current is essentially the charge, right? The total charge that it takes by divided by the time it takes, the total charge in the channel divided by the time it takes to traverse from one end to the another. Total charge is nothing but Cox times W times L, right? This is the capacitance times the overdrive voltage. It is the V overdrive. Let me write it as VGS minus VT. And what is the transit time? Transit time is nothing but the amount of time the electron takes to go from source to drain, right? So that is essentially L by V, right? And what is V? V overdrive by L times V. What is V? V is nothing but mobility times the electric field, mu times electric field. But note that now the electric field has saturated. It's basically E sat. In a long channel device, this E sat is a function of the VDS, right? The drain to source voltage that you have applied. But in this case, it is saturated, it is fixed, right? So you essentially have, what do you get? You get mu n, Cox, L goes, W times V overdrive times E sat. Okay. So what are the key takeaways here? The key takeaways is that you see that the current is no longer dependent on the length of the device, right? So if this happens only when this happens only on the extreme case when the entire channel is velocity saturated, right? And so it is always instructive to whenever you are designing something in a particular model, right? Whenever you are designing something in a particular model, it is instructive to test out your devices to see that where are you in terms of your IV characteristics of the MOSFET. Are you here or are you here, right? So long channel device, you see that there is a quadratic relationship with respect to the overdrive, and it is an inverse relationship with respect to the length of the device. In a short channel MOSFET where both the entire channel is velocity saturated, then you see that there is a linear relationship with the overdrive and there is no relationship with respect to L. And almost invariably you are going to see in modern technologies, you are neither in the long channel case, you are nor in the short, you fall neither in the long channel category nor in the short channel category. By the way, I'm talking about devices. I'm talking about most of these CMOS based bulk CMOS based technologies, right? So in these cases, then you will see that you are neither there nor here, but you are somewhere in between. But it's good to know what are the limits are. Okay. So if you are in this category, if you fall in this category, then what is GM? GM is essentially again dou I dou VGS, as essentially means GM is UN Cox W times E sat, right? And then what is omega T? Omega T is GM by CGS, which is mu n Cox W times E sat divided by, again, CGS is some factor, let me call it alpha times Cox times WL. So I'm not, note that in case of a long channel device, this factor alpha was 2/3, right? Because of the triangular approximation. But in this case, it's the triangular approximation is strictly not valid. Probably one should take 1/2. But I mean, it depends on the particular channel profile. So I'm just taking alpha, which is some constant independent of Cox, right? But the key thing to note here is that, I mean, we will not bother too much about this alpha and mu. The Cox gets cancelled, the W also gets cancelled. But the key thing here to note is that omega T is essentially some constant times E sat by L, right? So key thing again is omega T is inversely proportional to 1 over L and does not independent of overdrive voltage. Okay, so this, if you are truly using a device which is velocity saturated at both ends, then you are going to see a scenario where you have hit a brick wall in terms of design parameters, because L, if you choose an L which is minimum, cannot do any, you will not be able to go beyond that, lower than that, and you will see that your V overdrive, I mean the other handle that you have on V overdrive is also gone. However, there is no however. I mean, one might say that what is that ESAT? Now ESAT is essentially the saturation electric field that is also not in your control, right? So, but fortunately, you will see that you are neither, as I told you, you are neither in the truly long channel mode, or you are neither, or in the truly short channel mode, right? You are somewhere in between. So, in most designs that you will do, that we still do, you will see that increasing V overdrive will help increasing the FP. Okay, so that's essentially the key takeaway till now in today's lecture. So before we end today's lecture, I would like to point to something else as well. So if you recall, in the last lecture we talked about what if I take the common gate amplifier, or rather common gate configuration, and bias it in the source with an inductor, right? So then what we did, we were to ensure that the gate and the source are tied together. Okay. So what happens if the gate and the source are tied together? So even before going there, this gate and the source being tied together. So let's say the gate and the body is grounded, and let's not bother about the fact that the forward bias and all those things can happen. We are only I want to focus on the capacitance part of what happens if I connect the capacitance seeing into this node, right? So that's what I am bothered about. So again, if I go to the cross section of the device, P minus is grounded. Okay. So what do we have here? The N and the P all are these are essentially reverse biased PN junction diodes, right? These are reverse biased PN junction diode. So in a reverse biased PN junction diode, you have a depletion region, right? So you have a depletion region here, right? If I let the channel out, if I do not bother disturb the channel, I know that there is a depletion region here. If there is a depletion region, which means I have a depletion capacitance, right? I have a depletion capacitance between the drain and the body, or the source and the body. Right? If this is the source, it have a depletion capacitance with the source and the body, which means there is a capacitance. I have this capacitance. This is incrementally shorted. This is the CGS, and I have this capacitance, which is also shorted to the body, right? I call this CSB. Right. Similarly, you are going to have a drain side capacitance, but I mean, since we are only looking at the what is happening at the source side, this is of interest. Okay. So so what is the effective capacitance at this node, at the source? So effective capacitance at the source is CGD, CGS, and CSB put together, right? So your amount of short circuit current that is going up, right? So this is I out. So what is I out in terms of I in? If this is I in, so I out is essentially I in times GM by GM plus J omega CGS plus CSB. Right? Earlier it was only CGS if we had neglected CSB, which essentially means that your I out over I in is 1 over 1 plus J omega CGS plus CSB by G. Right? So as you can see, I mean this is obviously lower than this factor GM by CGS plus CSB is obviously lower than omega t, right? But fortunately, as it turns out, this depletion capacitance is much smaller than the CGS capacitance, right? Quite a few by almost like 3 and 4x, depending on which technology you are using, the CSB capacitance can be much smaller. So you don't get too much of a hit. But the issue is what happens if I use a triple well transistor, right? Because we saw that this type of biasing is problematic because the diodes can get forward biased, which means that we had to use a triple well transistor in order to ensure that we were able to do this. We wanted to ensure that the body and the source gets connected, right? So if the body and the source gets connected, so then what does the cross section look like? So then now the transistor itself changes. You cannot use a regular transistor with a common p substrate. We had to put a N well, right? Then on top, inside that, we had to put a P well, we call this P minus, and this new P well was acting as our tub in which we are making that isolated piece of transistor. So we had this gate, drain, source, right? So now what about the biasing? So this guy is biased always to ground. What about the N? What about the N well? This N well, again you see that you have a PN, the either side of the N you have a PN junction, and you have to ensure that both the PN junctions are reverse biased, which means that this N well has to be biased with the maximum potential that is available to us, which generally is VDD. So this is VDD, right? So, and what are we doing? What is the goal of doing all this? We wanted to ensure that the body of the actual transistor gets shorted to the source, right? So which means that this is N, this is P. So these two are shorted. Let me draw it slightly bigger manner. So this is P plus, this is minus. So these two are shorted. Okay. So now what? So which means that now, can you comment on this entire tub? Can you comment on this? It is a different color. Can you comment on this entire yellow tub? So is this yellow tub now at a constant potential, or is it also swinging? It is of course swinging, because what is this yellow tub? This tub, this source, this source terminal is essentially this source terminal, right? It is swinging. This guy is swinging, which means now the entire tub is swinging, right? So okay, so what's the issue with the entire tub swinging? Now note that there is a capacitance between this tub and this n-type this n-type well, right? There is this capacitance, and it is a big capacitance. It's not a small capacitance, because it's a big tub, correct? So now you are going to have a large capacitance and not small with respect to this CGD capacitance, right? So this CSB can be of the order of CGS, right? So which essentially means that moment you connect the body to the source, you are taking a frequency hit. Your FT of the transistor, or the effectively frequency at which you are going to get, you will be able to pass on the current from the source to the drain is essentially reducing, right? So this is usually another trade-off. As long as you are not going, I mean, let's say if I take some very crude examples, let's say your FT of the transistor is 100 gigahertz, which is not very uncommon which is actually quite common in today's technologies, and you are operating at couple of gigahertz, maybe 2 gigahertz or 3 gigahertz or even 10 gigahertz, you are fine. But if you take a 100 gigahertz FT transistor and you want to work at 20 gigahertz, then you really have to bother about, or even 10 gigahertz, you really have to start bothering about these effects. Okay, and in those cases, if because of choice of these architectures, if your 100 gigahertz FT transistor goes to 80 gigahertz, then it's a serious impact. Okay, so now depending upon what you are trying to do, you have to be conscious about your design choices. Again, it's caveat, it's not like It's not like you will be always be designing for at the edges of your performance that the technology is giving you, but it is always good to know what the edges of the performances are. Okay, okay, we'll stop here.